third lecture or second day. I'm going to show you again the ternary diagram, now with more details. Binodal curve separate the two-phase region to the single-phase region. We have a plate point. That's this point here, right? The plate point shows us a point where the two compositions of the separate phases are identical. They're exactly the same. It's the first position where you have a single phase, actually, where the binodal points are so close to each other that it becomes identical. We'll go further into that. Okay, so single phase region, two phase region. Okay, gasoline increases, we have all the regions here. And these lines here are called the tie lines. A tie line links two different compositions of two separate phases. Any composition, this is very important, any composition, if you pick one point here, here, any point in this line for example, all of them will create separate phases with the same composition. One water phase at this composition and another gasoline phase with this composition. Differences in that case is that although you have the same compositions for this phase and this phase, the volumes will differ, not the composition. They will have more gasoline phase or more water phase, depending on if you're closer to the gasoline, you have more gasoline, or if you're closer to the water and you have more water. Another important thing that you have to understand is this L0 here is the size, the maximum size of any tie line. This is because it's the size of the side of the triangle, right? That's why it's called L0. Any other tie line is going to be smaller. And you see that these tie lines, as you're moving upwards, they're more tilted to one side, right? And it's going towards this point here, which is the plate point. Well, they're becoming smaller, and as they're becoming smaller, so is the interfacial tension. As the tie lines are smaller, the interfacial tension decreases. So any compositions that you're adding, they're coming towards this point here before it goes to the single phase region of the diagram. So as we introduce more ethanol into our porous medium that has gasoline residuals and water, so basically considering that actually neglecting completely the dissolved phase of gasoline into water, we have a water phase and a gasoline phase. As we mixed with ethanol, some of the gasoline partitions into the water plus ethanol. But as we add ethanol to the gasoline, some of the water partitions towards this gasoline phase. So you have the three of them in both. Okay? This is very important, right? What we end up having is the reduction of interfacial tension in that situation. Take a look at the situation here. Compositions are at this end, as I mentioned. Repeating, the plate point corresponds to the situation where both phases, water and oil, have the same composition. This corresponds to interfacial tension 0. This presents an important conclusion. As the tie lines move towards the plate point, the interfacial tension between the corresponding phases decreases. Okay? So, in a ternary diagram, ideally, the smaller the two-phase region, the more efficient the process, since the overall fluid composition, gasoline plus ethanol plus water, is expected to remain within the single-phase region of the diagram. Okay? Well, we have some of the points here, and you see how the compositions are, the ends of the compositions. Those were measured on my PhD thesis. You may find it there. Take a look at that. I tried to use refractive indexes to correlate the compositions, which is a way of doing it. Okay? Take a look at the phase behavior. Phase behavior, as I was introducing compositions, those are the compositions in yellow. Bad choice of colors, I see. Moves towards the plate point here. Then you see two compositions, two compositions, two compositions, and so on, right? Well, the interesting thing is that the minimum amount of ethanol that I have to add to reach single phase is the one line parallel or tangent to the plate point here, touching the ethanol composition. So the minimum amount of ethanol that I wanted to add to flow with single phase region was 88%. So we added 100% ethanol to make sure we had enough ethanol trying to work and displace the ethanol. So we started with a composition of gasoline and water about this point here, and we moved to that point. I used 20%. Look at that. Okay? So this is the phase behavior that we have. Another thing that we had with ethanol, just interesting for you to understand, is that ethanol changes in volume as we add ethanol to the composition. I was adding ethanol to gasoline, and you see that the volume changes. You see, the volume decreases to 3.5% when we adding ethanol to the gasoline. So we made that measurements to see if we would create some empty spaces, and that was not clearly seen in the experiment. But you see a tiny white line forming. That's because of the shrinking of the products when they mix together creates a lowering of pressure, and you create like a small gas bubble to fill this 3.5% difference. Actually, we didn't have this much difference, okay? But we end up having a bit of a difference in that. Okay? Well, what is important for us to see here is this phase, this behavior. Look, this is the initial interfacial tension that we have between gasoline and water, right? About 22, 23 millineutrons per meter. Look, as we added ethanol here, look, the decrease of interfacial tension when we had 0.3 only of ethanol, right, or 30% of ethanol, not 100%, the decrease is huge. So we anticipated that we would have mobilization of that by decreasing by adding just a bit of ethanol. So from our measurements in a lab, we were really, really anxious to have that. Another way of showing this is by the capillary number. That's not of an issue in this part of the course. But as we show this capillary number decreasing, we tend to mobilize the ethanol. But this is a very, very promising situation that we measure in the field. And we'll talk about that in the next slide.